All right. Let's see if I did this correctly. Remy is in Australia. So I don't know if I just started this stream correctly or not. He is my producer and usually does all of this stuff. So let me know if you can see me. It says there are people here, but I don't know if that means that I am actually live or not. God, I miss Remy already. Okay, good. I hope it worked. Yeah. I'm having to do this solo tonight, so if there's like weird technical stuff, please let me know. And also bear with me because I'm having to do the software, talk, and show you all stuff. So yeah, tonight I'm going to be going deep. Remy's not here. Remy has a family. God bless him and his family. But because of that, he's got responsibilities as a dad, as a husband, as a fish tank owner, as a dog parent. I'm a college kid. And I've been a good boy today. I finished my homework. So theoretically, we can go as late as I want because the only limiting factor is me. I don't have any more homework this week. I've done it all. I'm up to date with my lab work. So we could go very late tonight and go down some rabbit holes and just talk about anything. I figure, yep, the parents are away, out of the doghouse. Remy is in Australia, So I figured I would start out with the topic that everyone is always talking about, and I would just talk as long as possible about it, and that is antibiotic usage. If there's anything else that we would like to see or talk about tonight, as I said, I'm going to be on all night, but looks like there's some people here already. I can just jump into it. So let's see if I can do this smoothly at all. I'm going to kind of start at a top-down level of here's what different bacteria are, here's kind of how we categorize them, here's the history of how these common antibiotics were found, synthesized, why they were made, what typical diagnosis looks like when you have a bacterial issue and then you go to apply antibiotics, how people are doing antibiotics wrong, the right way to do antibiotics. And then I'm also going to go over some Aquabiomics results from some very impressive tanks and show you guys the microbiome and kind of talk about ways that we can troubleshoot these issues with or without antibiotic usage. So with all of that out of the way, let's see if I can do what Remy does and successfully share my screen. Okay, tell me if all of you can see that and if it's like large enough. That large? How about that? This or that? A or B? Would you rather see my face or would you rather just see the screen? Which way is easier for you all to see? No fireball tonight. No. That will never happen again. A? Okay, you guys want to see my beautiful face? Now we got to vote for screen. Okay, next person will be the tiebreaker. My face or the full screen? We have a vote. We're 50-50 right now. Yeah, Josh can text my mom. Josh met my parents. We'll go we'll go full screen because there were complaints last time about being able to see everything. Okay, so let's just start off. Bacteria, they're small. They grow really fast. They grow exponentially. Here's kind of some common shapes that bacteria are found in. You've got your coccus, which is like a little ball. Bacillus, which is like a pill shape. Then you've got weird guys. You've got spirochetes. You got Spirilla, which are both spiral, kind of like, twisty guys. Then you got your Vibrio, which all of you should know about because it's the hot topic issue in terms of reef and coral associated bacteria. And they're kind of like a kidney bean. Then in terms of naming bacteria, just as a top level, you name them through their shape, then their orientation. So if you got two, you got Diplo. Strepto is multiple and typically in a chain. Staphylo is when you have them in a small little group. So kind of here, Streptobacilli, Diplobacilli, Streptococcus. There's lots of different ones that can be applied there. And that's kind of general top down how we can begin to categorize bacteria is through their shape and how they're grouped together as a larger unit. Now, there's more technical ways that are still conventional methods to categorize bacteria. And that's when we get into gram-negative versus gram-positive. You may be familiar with these terms if you've been around microbiology at all. If you are completely ignorant about them, that is okay. Microbiology is not for everyone, and it is also, It's typically something that you're only really exposed to if you're like, in a STEM degree. So I will do my best to break down these concepts for people who are completely ignorant about them. And if you have any questions at any time throughout all of this, please feel free to stop me and let me know if I'm doing a terrible job at explaining something, and I can go back and do my best to explain it in a better way. So that's the advantage of this being live. If I am not teaching something well, please tell me, and then I can try better. So this is kind of the typical way that we categorize bacteria in a broad sense is gram-negative, gram-positive. This has to do with the structure of their outer layer, their membrane, and their wall. Gram-positive bacteria have their initial plasma membrane, then they have a very thick cell wall made out of peptidoglycan is what this is called. It's kind of like a fatty acid type of thing, so it's a lipid. Then we have gram-negative. They have a very thin peptidoglycan layer, and they have a secondary plasma membrane. On the outside of this secondary plasma membrane, there are molecules called lipopolysaccharides, otherwise known as LPS, like the LPS coral. These typically are toxic and, can basically cause issues later on. But that's the main difference in terms of structure between these two bacteria. So how do we tell if a bacteria is gram-negative or gram-positive? There is something called gram stainings. This is actually a lab technique that you can utilize. So the goal here is to actually stain peptidoglycan. And based on the concentration of peptidoglycan and the location of it, based on these things right here. So gram-positive have peptidoglycan on the outside. It's exposed to the external environment, and there is a lot of it. Then gram-negative have their peptidoglycan layer kind of hidden, and there's not a lot of it. Therefore, if we apply a stain that stains peptidoglycan, this will be a different color than this because of the amount of exposed peptidoglycan there. So you basically add this stain called crystal violet, and then you add iodine, and that makes it so, the dye is more soluble, it sticks to things. You then add alcohol. Alcohol basically makes it so that any excess dye flows away, and if it's not bound to peptidoglycan, it will flow off the slide. And then you do a counter stain called safranin, which is designed to stain cell walls that are not peptidoglycan based. And basically, what this renders is gram-negative bacteria will be stained one color, and gram-positive will be stained a different color. And you can see this here. So gram-positive bacteria have that more crystal violet purple look, while gram-negative bacteria are stained by the counter stain, safranin, which is basically like a red or pink color. So looking under a microscope now, if you take a sample of a sick coral, something like that, with this basic knowledge in microscopy, and if you buy a gram stain kit, and this is pretty easy to do with enough practice, you can then get a general idea of what type of bacteria you're looking at. So you can say, okay, it looks like a bunch of these little, pill shapes together in a big line, and they're red. That means that you have gram-negative, streptobacillus is kind of the general top level name of what you would call that, to where then you can begin to kind of differentiate it in some ways. Now, that is not a hard and fast diagnosis by any means. It doesn't tell you much beyond that. It doesn't tell you what family it's in, what it eats, what species it actually is, anything like that. That mostly is relegated to the realm of DNA and genetics testing through things like Aquabiomics, the next generation sequencing, or, traditional sequencing methods like Sanger, things like that. If you isolate the DNA, that is. And then also doing types of growth assays with different media, things like that. So in terms of just visual acuity and categorization, these are two ways that you can apply things, and will at least give you a starting point, because this gram-positive versus gram-negative thing really allows you to begin to choose what type of antibiotic you would like to use if you're in a scenario where it is appropriate to use some. Now, as with all things in science, there are always exceptions to general rules. There are many bacteria that are not categorized as easily and do not belong to this dichotomy between gram-negative and gram-positive. Rickettsia. So this is a common coral pathogen that's actually found. Some in that family. You've got the spirochetes. These guys have too thin and flexible of cell walls for them to be really effectively stained via gram staining. You've got archaea. So archaea are not actually bacteria, but they still have 16S rRNA. So if you're doing like an Aquabiomics microbiome test, these are going to come up with it as well and you will see any archaea. Some of these can be coral pathogens. Some of them are good guys, but regardless, they will look like bacteria for the most part. They can be sequenced like bacteria, but they will not respond to a gram stain like bacteria. There's also, Mycobacteriaceae, so like mycobacteria. These guys also don't really take well to gram staining either. So there's a lot of other types of bacteria besides the common gram-negative and gram-positive that kind of reside outside this typical categorization. Now, these are relatively low in concentration compared to most typical bacteria, which are going to be gram-positive or gram-negative. So this isn't something to worry about, but rather something to be aware of. If you get a weird instance to where you perform a gram stain several times, and it's not user error, but simply something's not staining, it may be because it's part of one of these groups or several others that exist as well. So let's go into kind of the history of antibiotics now. So antibiotics, if we're looking at the Latin word, means against life. These are compounds which have been basically found in nature and harnessed and purified and are now mass produced that are designed and have the ability to kill different types of bacteria. Now, there's a variety of different mechanisms through which antibiotics can work to inhibit or slow down bacterial growth or outright kill them. That's kind of like bacterial static versus bactericidal, that little debate. What we will start with quinolone-based antibiotics. So these are things like oxalic acid. I'm mostly going to be talking about oxalic acid and ciprofloxacin in this because these are two of the hot button antibiotics that people are starting to throw at their corals and have been for some time. So oxalic acid and all of the quinolone-based antibiotics were discovered in the 1960s. So there was a group that was doing research on malaria, and they were attempting to find an anti-malarial drug because malaria kills a lot of people every single year. Very, very virulent and, bad disease. So they were using chloroquine, like chloroquine phosphate used to quarantine fish with, as a precursor molecule and attempting to synthesize different types of chloroquine-based antibiotics from that. Now, what this yielded was basically all of these different chemical groups right here. So this was the first one to be discovered. After that, oxalic acid and all of the rest of these were synthesized. So for a period of time from the late 1960s to the mid-1980s, quinolone-based antibiotics that were derived from this lab and from this anti-malaria research were kind of the bee's knees. They were used in most general hospital settings as the go-to antibiotics. What began to happen, though, is antibiotic resistance took hold. This now required some ingenuity and some innovation in terms of this general structure. So they kept the quinolone-based structure, but they decided to add a fluorine atom to it. So Cipro was approved by the FDA in 1987. Basically, like around 1991, they started making, I'm like choking on myself here. They started making like injectable versions of it. So if you look at the chemical structure of, quinolone-based antibiotics, ignore the fluorine here. This is actually like a pretty wrong. Here we go. That's a little bit better. So that's kind of the general structure. You got these two cyclohexanes, and these are variable R groups. And then with the fluoroquinolones, they then added this fluorine atom. Now, the fluorine atom is very interesting and allowed for several things to happen. So fluorine has the ability to bring an entire chemical through a fat, through some lipids. So the quinolone-based antibiotics are able to target and do very well at disrupting gram-negative bacteria. But to get through this very, very thick wall of peptidoglycan was challenging for that type of chemical structure. The inclusion of fluorine as a variable carbon group on that structure allows for now the fluoroquinolones to go past, in most cases, this barrier to where now the activity to inhibit bacterial growth is with gram-negative and gram-positive bacteria. So basically the mechanism through which this happens is let's see if I thought I had a diagram of it. Maybe I don't. I'll just look it up. Topoisomerase 2 and 4 inhibition, quinolone-based antibiotics. I thought I had this already to read. I guess not. Okay. So let's see if we've got like a nice little, here we go. So topoisomerase is an enzyme that basically helps unwind and rewind the DNA during DNA replication. This is a conserved enzyme that most all bacterial species have to utilize. Now, what quinolones or fluoroquinolones do is they go and they're super sticky and have a high affinity for this enzyme. They then stick to it. What this means is that they cannot do their job. It inhibits the ability for topoisomerase to unwind and help process this DNA. Effectively, after several generations, this means that the bacteria cease to reproduce. It eliminates them from the population. If you've got a pathogenic bacteria that is susceptible to a quinolone or fluoroquinolone, and you have it come in and inhibit topoisomerase activity, that means that it can no longer replicate its DNA and no longer reproduce. So eventually it just dies off and is not part of that system. This is a broad level overview of how cipro and oxalic acid both function as a chemical to inhibit bacterial growth and how they are bactericidal. At lower concentrations, they could be bacteriostatic to where they stop growth, but there is not enough of the molecule to completely inhibit, basically the topoisomerase activity throughout all of the cells, or at least all of an individual cell, which means that there's slower bacterial growth instead of just having it be bactericidal. So this is the importance of concentration. So I guess I have another slide for this. So Kirby-Bauer test. This is basically how we begin to decide what the concentration of an antibiotic is. So we have gram-negative versus gram-positive through gram staining. Therefore, that we can then begin to choose an antibiotic which is effective against either gram-negative, gram-positive, or is broad spectrum and affects both. And then we have to determine, okay, we have our chemical families of interest that can begin to inhibit this bacteria. Now, how can we determine what dosage that we use to kill this? So this is a simple test called the Kirby-Bauer diffusion test. Basically, you buy these mass-produced little discs, and the discs have antibiotics in them of a given concentration. And then you will plate and grow the bacterial pathogen of interest on a petri dish. Now, in the middle of that petri dish, you then place these different discs, and based on what's called the zone of inhibition, this area where there's no growth, the amount of space here correlates to known dosages and concentrations of the antibiotic. So you can see whatever antibiotic this is was not very effective at all against this bacteria. This one did not work at all, but these ones did a very good job. This one probably the best right here because there's very clear defined boundary of clearance compared to the kind of foggy layer here. So this would be like the antibiotic you choose to then begin to inhibit this bacterial pathogen or bacteria of interest. So then you could go and do the math and do the calculations. So you got your bacteria, you have your antibiotic, you know your bacteria of interest, and then this gives you your dosage. After that, you can begin to do more defined studies with liquid suspension cultures to where you use spectrophotometers and things like that. And then you could determine the contact time needed to eliminate this population. That's a little bit harder to show you all with a picture, but basically you would take this from a solid medium of growing it on a plate, and you would grow these cells in a dense broth, so like bacterial broth culture, like a liquid culture. Let's see, there's a picture of this so you can understand. So so here's that's not a good picture. Yeah, it's going to be pretty turbid. So you'll start out with kind of like clear broth. Then as you see bacterial growth, you'll have this turbidity form. So the actual cells, there's a very good one right there. So you can see this kind of difference in growth over time. Basically, you can measure how turbid, how dense, how unclear this solution is using a spectrophotometer, which is like the same technology like the HANA testers use. So it's just like a beam of light that comes through, and then there's a detector on the other side, and the interference with that beam of light tells you how dense or how turbid that solution is. So you can begin to add this antibiotic of interest that you've chosen that seems to be the best in inhibiting it using this step. And then over a course of time, you can record how turbid this becomes or how turbid it does not become. So the appearance or disappearance of turbidity based on if you have existing cultures or you're growing up cultures. So you would just add varying, like that concentration, and take, varying time points and to see how long it takes for that antibiotic to be in contact with that bacteria. And then that gives you your contact time. So basically with human medicine, we've been using these chemicals for long enough to where we have general schemes for application. So if I've got strep throat, they know what antibiotic they're going to put me on. They know how long I'm going to be on it. They know exactly what times I'm going to take it, etc. Now, this is something we don't really have information about with coral, which is why common applications of antibiotics are very, very dangerous and reckless in terms of what's happening in the hobby right now. Take a drink of water. We've been talking for like 20 minutes. Hey, what's up, Sarah? Yeah, I would love to go to Cornell. I really would like to. That'd be awesome. Yeah, I heard there's like a program they're trying to put together there. That'd be great to get a team of people to go out and try to build some curriculum or talk about coral and disease to people. That would be awesome. I would also love to go to New York. So yeah, if you've got details on that, please let me know. I would be highly interested in that for sure. Okay. So let me open up a Word doc. Let's see if this lets me share it. I will try my best. Now you have to see my face again. Share screen. Okay. So based on what we've just covered, there are a couple things that need to happen if you have a suspected bacterial infection in terms of diagnosis. So one, determine if it's bacterial. So this could require, like if you've got an open lesion with recession, you could look at that, you could analyze it, you could look under a scope and see if you can visibly see bacteria. If it is indeed bacterial, then culture the bacteria. This can't always happen, especially with coral, unfortunately, but let's assume that it can in this instance. Once you have a bacterial culture, you can then go and do gram staining. So that was what I covered earlier. And then you can see basically if it's gram negative or gram positive. You also can have a simple morphology at this step. So seeing like, coccus, bacillus, spirochete, etc. You wouldn't be able to do spirochete, gram staining with that, but you know what I mean with the intro if you've been watching this whole time. After this, if you know it's gram negative or gram positive, you can then, like, you wouldn't have to do this if you know what you're doing, like literature search for antibiotics, right? So, I mean, that's something you should know if you're doing this quite a bit. You would have options that are already available to you. But if you're completely new to this, then you would say, okay, what antibiotics can I get a hold of that can affect gram-negative bacteria, if that's the type of bacteria that I've cultured? After that, you can do the Kirby-Bauer. I can't spell. The disc assay, and you can order those Kirby-Bauer discs, have a Petri dish, and then you can determine the concentration that's needed. After that, do turbidity / contact time assays. And after doing all of that, one, what the bacteria is and simple things about it. Roughly, you don't have the exact ID without genetics, but the shape, the size, the growth rates, if it's gram negative, gram positive. 2, what antibiotic it is sensitive to. I can't spell still. It is sensitive to. Oh my God. And then what concentration and time to apply this antibiotic at. All right. Now let's talk about common methods in the hobby. The hobby. What do we do? 1, I see brown jelly. 2, I throw in Cipro, erythromycin. Pretend that says erythromycin. I don't want to go back and correct it. Amoxicillin. Also iodine for some reason. Also sometimes hydrogen peroxide. Oh my God. I can't spell. My keyboard is also broke. I don't have a G key, so it's like pretty hard to type. Then also I like amino acids. And they make me feel warm and fuzzy. And I use them without question because everyone on Instagram says they are awesome. And also they glow green. Smiley face. Right? So that's peanut butter too. So that's the typical, what we do in the hobby. This is like the right way to do it, right? This is the process of how you would determine a bacterial pathogen and then have a effective treatment for it. In the hobby, we see a symptom and we do all of this. And that is very, very bad for a number of reasons. And as you can see, there is a very large disconnect between this stringent process and whatever is being recommended by gurus on Instagram and Facebook who claim they know, but they simply do not. So, assumption one of this. Brown jelly has one bacterial pathogen. I'm going to tell you right now, it doesn't. Plain up. I'm going to tell you it doesn't. So that's assumption one is bacteria, it's caused by one. It's caused by bacteria. Only bacteria. That's it. Yep. So it's got to be bacterial in origin. That means that we have to use an antibiotic. Second assumption is, actually, I guess this isn't an assumption, right? So they don't assume it has one. They don't even ask that question. They just say, this looks bad. Let me throw everything at it. Because I don't know. Right? No one can tell you right now what the root cause of brown jelly is. Part of the reason for that is because there is no root cause, which you'll eventually get from, me if I get a paper or I just release my research. I'll go into that a lot more later on. It's a polymicrobial thing. It's a mess and it's very complex and is not simple cut. But the solution is not throwing every single thing we have at it and seeing what sticks. There still needs to be the general guidelines in terms of applicability. So there's ways to do diagnosis by looking at the microbiome of the tank, by taking a swab of the jelly itself and seeing the microbial composition, by having an understanding of the good versus the bad bacteria in that sample. There is a misunderstanding that all of the bacteria that are in that sample, in that open wound, are bad. And that is a very big misunderstanding. So, from this, I'll go more into brown jelly later on and basically go on a tangent about how everyone is very, very wrong about this. But I will go into kind of what the diagnosis side could look like so you have a better idea of what I'm talking about first before I get ahead of myself. So let's look at 2 Aquabiomics tests that I was sent this week, both of which are very, very interesting. And these can kind of provide the basis of, problematic systems and what they can look like. And these are 2 very different cases of how a system can be problematic. So this one comes from Chris Kapp at Aquatic Art. Very, very good shop. Very intelligent man. Very good reefer. He's been doing it forever. He started a new display tank. And basically he used only dry rock, dry sand. I think he added like a little bit of existing live rock from another system. He has a UV sterilizer. He runs ozone. He utilized antibiotics and cut the base on all the coral, I believe, before he introduced them. So he was very meticulous, very good about quarantine. And as you can see, this has some of the lowest diversity and balance in terms of the entire Aquabiomics database. Here's your typical sample, the average of all samples. Here is his. It is dominated mostly by this J115 strain, and there's not much else. There's 5 bacterial families that are pretty much present, which is like the least diversity I've ever seen in a sample. Like, many of you that watch my content know that I consistently rant about how dry rock, dry sand is not the way to start a system, and that we're really beating ourselves up in terms of the diversity that we're adding to our tanks. But this one takes the cake. And the thing is that Chris is a by the textbook guy. He is very meticulous in what he does, and he follows everything to a T. So he basically took the modern method that is being preached by BRS, by Worldwide Corals, by everyone out there telling you to use dry rock and bottled bacteria, and he did it to the fullest extent. And look at the impact on the microbiome that it had. You can see this is an absolute desert, ecological, disaster here. Like, there's just none of these good families. You don't have any of the Plankton families. There is just a lot going wrong here. And this is a very unbalanced microbiome. So first I will show you, here's the tank. It looks awesome. I saw it in person. Acropora colonies are amazing. He had like a Walt Disney colony. He had a bunch, I think he had some Speciosa in there. Beautiful Euphilia colonies. The coral are doing very, very, very well. So this also is more evidence for my point of just because you have a very bad microbiome does not mean you're screwed. Now, you are certainly working an uphill battle here, but any of these pathogenic events are always going to be preceded by an abiotic stress event. So if you watch the huge breakdown where I talk about dimethylsulfonylpropionate, infochemicals, DMSP, the whole metabolomics thing, and the general pathway for how coral disease happens, you are always going to have a stress event, which then causes the good guys to die off on the coral, which then causes DMSP and other infochemicals to build up in concentration. And then you will have the unbalanced microbiome kick in. At that point, you'll have pathogens come in that will quickly deal with the coral. That'll manifest as jelly, as RTN, as STN, whatever. Or you'll have a more slow decline to where none of these good guys are in the water column. Therefore, the coral cannot reacquire them. So Chris shared with me that this system is very good, but periodically he'll get bouts of jelly or RTN, things like that, to where, and as well as that, there was a very, very prolonged ugly phase. It took him a very long time to get this tank dialed in and starting to look good. So it took much longer for this tank to reach any type of, biological equilibrium. But B, despite the corals surviving, he thinks that they could be thriving, quite a bit better. Chris, I'm talking about your tank right now, actually. Perfect timing. I was just talking about it. I'm going over your results right now. So this basically goes to show that despite having this poor of a microbiome, the tank still looks fantastic. Now, when it comes down to something like this is the difference between surviving and thriving, right? So I think that Chris could likely get faster growth rate, better polyp extension, fleshier, like membrane growth on the euphyllia, things like that, if the microbiome were balanced. And more importantly, he's going to have a lot more wiggle room. So one small swing can be a disaster in a system like this compared to this. There's a lot of species that will metabolize those infochemicals, like Pelagibacteriaceae. There's a lot of good guys that can go in and directly outcompete some pathogenic families, things like that. This and having the correct microbiome works in tandem with the chemical side of a system to give you a much better buffer zone. And it means your corals are much better off in terms of nutrition, immune response, nutrient cycling, all around will have better health. This does not mean you can't have a successful tank. You obviously can. But I think if Chris chased this as a dragon, since he's got everything else dialed in and he's the man, he would see much better results. So also no coral pathogens. So that's very good. This is a good example of a tank to where, he did microbial quarantine. He just did it a little bit too well, I think. Chris, I would definitely probably seed, you have your SPS flat system. I would take, a bunch of rock from there, maybe even do a water change from there and kind of do like a transfusion. That was something you mentioned. I think it's a great idea. I think, because you don't have any fish pathogens or coral pathogens, I don't think there was any fish pathogens the last one. I can't remember though. Then I think that it would be pretty worth turning off the UV and the ozone and then letting some of these waterborne strains really grow in concentration. And I think that even if you did those three simple things and then you sent out another Aquabiomics test in 2 or 3 months, you would see a much, much more diverse community here. It might not be perfect, but it's going to be much better than this, I think. And the problem is there's not a bacterial product on the market to where you can add this in. So it's likely going to come down to adding live rock, live sand, or existing live rock. So that's kind of the more controlled way to do it because you already know the microbiome of your SPS flat. What you could do if you're more ballsy, though, is you could add a bunch of like Aussie live rock straight from the ocean stuff, but that comes with its risk of potential pathogens. I've done lots of real controlled testing, but I will not talk about that. All right, so this is kind of example one of how a microbiome can be somewhat skewed. You're going to have low diversity, but you don't really have much presence of pathogens, so that's good. This can mostly just implicate the corals in terms of long-term health. Now, this one is from Ben Johnson. Shout out to Reef Beef. You should go watch him and Rich. And this is one of his client systems. And as you can see here, nearly 50% of the tank is all Vibrio. Known coral pathogens, known fish pathogens. He's got Arcobacter in there as well. This is the one that's been associated quite a few times with, jelly with RTN. It is a good indicator, at least we believe, of the pathobiont. It is not the sole or root cause of these bacterial issues, but it is a pathogen that is known to cause these issues and be associated with it. So in this instance, this is a little bit of a tougher cookie to solve, simply because A, there is the lack of good diversity, just like Chris's sample. There is basically no Pelagibacteriaceae, hardly any Flavobacter, things like that, and things that make up that natural picoplankton that you're going to want to see. No Oceanospirilleae, things like that. So there's not Seascape Studios, because I am in college and I have been working on this for about 4 years, and I am hoping to get it peer reviewed, and it is something I am doing as official research with my university, not things I am messing around with as an independent person. So the peer review process, as well as the intellectual property associated with all of that, is a very stringent thing that has to go through several different guidelines. If I were to publicly share any of that, that could jeopardize the ability of getting a paper, or me having the rights to that intellectual property to where I could take my research to something like graduate school or a doctoral program where I could continue it with better money, better people working with me besides a small college in Kansas. So I have done lots of real and controlled testing and have lots of data, but those are not things I'm willing to share right now because of all of those potential legal and intellectual property stipulations. I can share broad ideas that I have uncovered with you, which is kind of what all of these streams are about, is alluding to some of what I have found and applying what I can with things that are open source. But yeah, I will not be sharing what I am doing. So hopefully you can respect that. Yep, coral can have fungal infections, Tim. Yes, they can. They're pretty wacky. So in this instance, a lot different scenario. There's it's the double-edged sword of having low good diversity and lots of bad guys. So this is an instance to where an applied antibiotic in a very limited fashion might be useful. Now, I do not advocate for antibiotic usage hardly ever, but this is an instance to where we have fairly clear diagnosis. We've got known pathogens that are associated with a lot of bad stuff. Having that high of a concentration of Vibrio, probably not good. Vibrio get a little bit too bad of a rap. There are some species which are good that are actually involved in the immune response of corals that are purely symbiotic. But the majority of the species in this family are opportunistic or purely pathogenic, meaning that the likelihood of some of these guys being bad guys is relatively high. As you can see, there is a healthy amount of Vibrio that can be in a system, but having this amount is outcompeting a lot of these other guys and probably not too good. Now, keep in mind, this tank is ran by Ben, also a very healthy and beautiful system. So the commonality between both of these systems I'm covering today is that both of them have a very wacky and messed up microbiome, but they're also managed by experts in the game. Chris Kapp and Ben Johnson have been around forever. They have been proven to have successful systems. You know, Chris has had an LFS for I don't even know how long. If you see her, I'm sure he could tell you. But, you know, I've been to a lot of different LFSs around the country now. And Chris's is in the top 3 for me. Like, it's right behind TSA in terms of aesthetics, in terms of health. Like, it really is just a very, very clean shop. Ben has been doing tank maintenance for forever as well. And he's got many, many successful systems. He's helped a lot of people and maintains many systems. These are people who are experts. They have blue thumbs. They have years and years of experience doing this. And that's the commonality here, is despite the fact that they might have a messed up microbiome, these people know what they're doing. They're good at maintenance. They're good at ensuring a tank is stable. But not everyone can be perfect. Not everyone can be Ben or Chris. And that's the importance of chasing a better microbiome. As I talked about before, this is a slippery slope. You're on thin ice here. If you've got a system that has a profile like this, all it takes is, one bad instance, and you could have a very, very nasty pathogenic event with this many known pathogens here. So basically what I talked to Ben about is sampling over a course of time. You never want to be hasty about preemptively or kind of prophylactically applying antibiotics, as they are not to be used lightly for several reasons, which I'll go into relatively soon here. So because everything is healthy, there's not kind of a fire to put out. that means that over time, doing regular maintenance, adding into other things like that. Look into DOE, the presence of noise. Best of luck. I believe you are leading new reefers astray. I disagree with you. So sorry, you do not believe that I am doing a good job. We can agree to disagree there. Anyways, so yeah, basically this, having several time points here in terms of several months of data showing how the microbiome could change. If he turns off the UV sterilizer, does Pelagibacteriaceae come back in concentration? If he adds Aussie live rock, does that change things? If he feeds, different types of associated bacteria in the market, if he adds PNS, things like that, those are all different trials we talked about to where he could see how the microbiome could shift in a more natural or controlled way. So if, there ever is an issue that arises, that could be the time to use the fire extinguisher of Cipro, of oxalinic acid, things that are known to be able to knock out Vibrio and other gram-negative families at a relatively low concentration to where they won't wipe out the nitrifying bacteria. Having a very limited and controlled dosage in that instance is something that I think that, Ben could do with reasonable confidence in this instance, given the microbial profile of this tank, especially if this large family stays consistent among multiple samples over basically a function of time. But if the tank is doing well, you never want to push things. I think that that's, kind of where antibiotics come in here. There's a very, very fine balance between using them at the right time and not using them at all, right? So stability can go a very long ways, despite the uphill battle of an improper microbiome. And there's likely longer-term, more healthy, natural methods, ecological principles to adjust these things. So for instance, even just like removing excess detritus in the sand bed can help, eliminate some of these biofilm producers, things like that. Adding in live rock and getting more microbial diversity incorporated into this family, knocking out UV sterilizer, some of the waterborne good guys can begin to grow. There's many more long-term strategies that can be chased and achieved here to have microbial management. You basically only want to use antibiotics as a last resort, or if you are very, very confident that the only issue that's causing a problem is the microbiome. And there's many other things that could, having your traces off. Like if you've got not good concentrations of halogens or any of the major or minor traces that are known to be associated with coral growth that corals can readily uptake over time. That's one thing. Having instability, having large swings in alkalinity and phosphates and nitrates, things like that. There's many other proximate causes that can lead to poor coral health besides just the microbiome. But the microbiome is a complexity and kind of a complicating factor in terms of all of this. So as I said, this is kind of your buffer zone in terms of how much you can swing and play around with your system if you want to chase things and things like that. The biggest thing right now is that, oh my, looks like I'm oversaturated. How did that happen? I don't know how that happened. The biggest thing right now is that not a ton of this is directly actionable. The dry goods market has not picked up and caught up with this. So we have the testing now, but there's still no true probiotic bacteria on the market that are coral associated. The only thing we can do at this moment is just have have removal. There's no addition yet in a controlled way, right? We want that controlled diversity of adding in that mix of good families and then trying to decrease the concentration of bad ones. And right now we have the crapshoot of we can get live rock from different locales or live sand from different locales. And hopefully some of those good guys will come in on those surfaces. Let's see. The turnaround times for Aquabiomics makes it less than ideal for use as a diagnostic. I can understand, though, it's not intended to be used that way. Yeah, so that's the thing with Aquabiomics is it's more of something to get an established baseline. One of the best ways to, one of the best times to sample is when your tank is doing very well. So if your tank is really rocking and you're seeing very fast growth and things like that, then that's a good time to see if there's a correlation in the microbiome or at least see what your microbiome is doing at that time. But having, monthly testing or at least every other month, having regular testing, kind of similar to how ICP is played out right now, would allow you to have a very good idea of how your system can change over time and how changes in your routine, your general maintenance, things like that can play into the microbiome, because all of these things, it's a very complex, dynamic biochemical system to where these bacterial families are likely to respond to whatever changes you make on the chemical side or just the maintenance side. Even if it comes down to how often you scrape your glass, that can impact some of these families that are, that form biofilms and live on surfaces, or could be associated with certain algae families. I mean, absolutely everything we do to our systems can impact the microbiome. So having a good record of that over time can allow you to know if there's any skeletons in the closet, in the instance of Ben's client system there, to where there's a lot of bad guys, to where if something goes bad, it's probably a good course to take action. Or in the instance of Chris's, to where there's just not many good guys. There's not really anyone bad. There's not anyone good. There's just not really anyone home. And in which case, that could probably be made to be better too. So that's kind of the microbiome thing and antibiotics. You really only want to use antibiotics as a last resort if you have a good idea of what's already in your system. Applying them willy-nilly, just if you see brown jelly, if you see, like ECS, like the elegance coral disease, if you see zoopox even, there's many other ways that you could begin to address those things. So, yeah. And like what Chris just said, the bottled bacteria on the market, you basically have Bacillus subtilis and Lactobacillus, which are terrestrial strains, which likely are either going to outcompete many of the good strains for resources or not stick around at all. For instance, Lactobacillus grows in acidic environments like the human stomach. They're not going to be growing and reproducing very well at all in an environment that's buffered to 8.4 pH plus in an ideal world. And then, the other types of products are just nitrifiers. And these are things I talked about in my last Reef recap, where I went over, all of the different beneficial bacteria, what a probiotic looks like, what probiotic coral, can look like, and things like that. Yeah, the tests are still steep in cost as of now, but Eli is actually the cheapest on the market out of any third-party company that does next-generation sequencing. So, for instance, if I wanted NGS stuff, where you see the whole microbiome, right, like that, the high-throughput samples like he does for any of my research, if I reached out to actual academic companies, they're double, triple the rate of Eli. So Eli, while it seems expensive to the hobbyist, in terms of the actual application of the technology, he is below all of the competition by an astronomical amount. And that's why I'm using him. Like, the service is exactly the same. It just comes from someone who's not innate to the DNA processing world, and instead is in a market that is a little bit more isolated and niche from anyone sending lab samples. But the cost is the same and the technology is the same. So my research is going through Eli, to be processed. Yes, so live rock and live sand as of now is probably your best bet. Now, there could be potential pathogens that come in on that live rock and live sand. You certainly can't control for the unknowns of the ocean, but you're also going to have those good guys. And there's not really any other way to get those good guys right now, especially things like Pelagibacter acae, and things like that. Here, so S2, here is the link to Eli's site. So Aquabiomics is the company. I just sent that in the chat. And then, Hydrospace is also good, right? So Ken is great. He has the PNS stuff, but that's a relatively small portion of the microbiome that we need to remedy. So he's got, the Rhodobacter acae, the good guys there covered to some extent, but there needs to be a lot of expansion in the market in terms of covering these families in monocultures or mixed cultures. The only bacterial product I know of on the market that has some of these guys is Biodigest, but Biodigest also could potentially have pathogens in it. There's high concentrations of Vibrio. I have not seen the family breakdown on that. And I would also like to see the family breakdown on multiple samples to see if they have a consistent manufacturing process where the same strains are incorporated into every single vial. So, yeah. The problem with getting live rock or live sand from a well-established system is that, if you don't know the baseline of that system, you could be adding in live rock or live sand from a system as bad or worse than the Aquabiomics test I showed you today, to where it's just riddled with coral pathogens and there's not really any good guys. Second, many of these bacterial strains will typically die off in our systems over time due to our current practices. So for instance, UV sterilization will kill any of the waterborne picoplankton, which are seen as one of the most beneficial families to have at this time. So, theoretically, if you had a existing system that you knew the microbiome of and it was good, you could definitely seed live rock and live sand from that system. But it's a question of what you already have in that system and what practices you've done up until this point to maintain or, basically have that microbial diversity. So in the instance of Chris's, shop, he had an SPS flat that had a lot more diversity than his existing display system. So he could go and take rock from there and put it in his tank, and he would likely get some good results from that. So that's an instance where both tanks' microbiomes are known. So something of a transfusion could be, applied relatively easily. But you need to kind of know. It's the same idea of not dosing what you don't test for. If you don't know what the microbiome is in that tank, you might not want to go and preemptively seed a new system with that microbiome. So that's kind of that. It's we need to probably apply a lot of these chemical parameters and huberises that we have, metrics to the biological side as well. So what's up, Chris? But that's my little rant about antibiotics there. So the history of quinolones and fluoroquinolones and oxalic acid and Cipro and when to use them, when to not, the issues with existing methodologies in terms of treatment, when would be a good time to apply antibiotics, things like that, what the typical route in a lab setting is for diagnosis and determining minimum inhibitory or bactericidal concentration, and things like that. So, yeah, if there's any questions revolving around any of that, let me know. I can talk about whatever. If there's not much engagement, I can call it a night. We can go as late as we want, or I can end it whenever. So, okay, Chris, let's have a little thing like we did last time. I'll play devil's advocate here. Why no Cipro? Why do you prefer to use oxalic acid compared to Cipro? What is your take on it? So that's what we're hoping to figure out with the community science project, Chris, because right now there's not any data to show what carbon sources could correlate to what families increasing in concentration. Like for all we know, vinegar could be feeding only Vibrio, right? We have no idea. So hopefully in about a month or two here, after we get all the data back, then we will have a good idea of if any of the common carbon sources could be something beneficial to add to a system to where it could be another natural way to regulate the populations of these things. So that's that. If you have a system you want to do that on, I can send you the sign up link because it'd be great if you could help with that for sure. Or if anyone wants to work on the community science project with carbon dosing, I can send the link to that in the chat. And there is an application there, but that would be great if anyone is currently not running a UV sterilizer and they would like to experiment with carbon dosing and get some free Aquabiomics testing and be part of community science. Here is the link to it. There's likely a pretty big difference. So a lot of these marine bacteria and bacteria in general will selectively uptake one carbon source preferentially to other ones. So for instance, like Pelagibacteriaceae, you really want to have like pyruvate is you can use like a sulfur source and things like that. There's defined medium that they do most efficient, do the best on. So theoretically, the different carbon sources that we add to our tanks, like acetic acid or like ethanol or methanol, in the case of like Nopox, there's different average concentrations and ratios of carbon per volume of that. So like methanol, Nopox is going to have a higher concentration of carbon per milliliter than vinegar is. So there's that. There's concentration of carbon source. There's also just the chemical structure of the carbon source and which bacteria can preferentially use that. And likely there is some that will, use it more than others. The question is, are those ones that do it good or bad? Okay, that's a good argument, Chris. Yeah, that makes sense to me. Yeah, I was going to say that. I mean, they're very, very similar in structure. The only difference is just, Cipro's got the fluorine, which means it can act against gram-positive, where oxalic acid is pretty much, just gram-negative, and that's good in some instances. I think it's a little bit more targeted in that way, but that makes sense. Yeah, because it's probably going to be regulated pretty soon. I mean, it's been used in the aquarium industry since like the 80s, I think, like with fish in like Norwegia or something. I was looking at the history of oxalic acid and its usage outside of just like pharmaceutical stuff, and I came across that. I thought that was pretty interesting. Remy decided to thug it out. Remy is deciding to optimize everything else before worrying about the microbiome because he's not seeing any obvious things that can be related to that exclusively. So yeah, I did not know that Chewy could no longer sell Cipro. I think that's probably good. Yeah, I really think that is good. I think there should be regulations on antibiotics for the most part. I mean, it's pretty dangerous that people can use these willy-nilly with no discretion, and it's certainly going to fast-track resistance happening, especially, like people use these and apply them like to human medicine too. Like antibiotic resistance is no joke at all. So I definitely agree with that. To everyone's dismay who loves the KFC dip and will probably hate me for saying that, I think it's likely the responsible thing to do. Yeah, this became the no Cipro show. Like so, yeah, it's very similar. Like it and oxalic acid both inhibit topoisomerase. They have like the same mechanism, same type of drug family. Cipro just has a fluorine on it, so it can also affect gram-positive. Besides that, the rest of it like has like a little bit less of a contact time needed to be effective, and it's a little bit better at antibiotic resistance occurring, but not much better. And those are really like about the only differences there. Zoonotic coral pathogens. Yeah, I'm sure they exist, right? So maybe not exclusive coral pathogens, but there's been plenty of people, like there was the one guy who got the mycobacteria infection and had to get his nerves scraped. Like that's pretty scary. And the thing is if we're using antibiotics in our system, then we're likely any potential human pathogens are also becoming resistant to them, which then means you go to the doctor not just with a weird infection they might not be able to identify off the bat that you might not even link to it being from your system, but it also could already be antibiotic resistant. So yeah, definitely using antibiotics willy-nilly in our systems could have downstream impacts on our health, the health of anything living in our home. And yeah, I mean, that's another thing is disposal, right? So these things have decent half-lives, and if you're not exposing them, you could add bleach, you could add like UVC, and that can break it down, like a UVC bulb and have it, or just run UV through it if you have like a little setup. But yeah, this should be, yes, it's common sense. You should, if you do not have evidence that you need something, you should probably not add it to your tank. Don't dose what you don't test for. If you've got a microbiome and you don't have any known pathogens, then probably don't preemptively go and do that. Yes, I talked about biodigest shortly. Yeah, it could have pathogens. It's got a decent population of Vibrio. The question is what species of Vibrio are contained in it, and is that microbial profile consistent based on their manufacturing process? So it would likely require, I'd like at least triplicates to go out, right, of a biodigest from multiple different batches, kind of blind from 3 different stores, and then send it off to Aquabiomics, and you can request the species level breakdown from Eli. He won't do it for everyone, but if you ask, he will, because it's all automated. It'll generate it anyways, and then we could actually see what species of Vibrio are contained in the sample to see if they are ones that are symbiotic or benign, or if they are some of the more opportunistic or pathogenic ones. So biodigest as of now seems like the best option in terms of a bottled bacteria, but there is that potential concern. It does have a lot of the good guys, though. It's got some Flavobacter. It has Pelagiobacteriaceae. It's got Osteospirilleae. Those are 3 families that are very important in terms of, having coral remain healthy for a number of reasons. They're the picoplankton, they make up nutrition, they metabolize infochemicals, and they outcompete pathogens. So having those in your system, very good to have. UV takes them out. That's why I don't like UV as well. Yes, I also doubt that most have disposed of it properly. I don't really see anyone talking about that. What's up, Logan? So the thing is, Jessica, is that most of the bottled bacteria on the market are not coral associated or even saltwater strains. Almost every single product out there, besides basically Biodigest and Hydrospace, are just Bacillus subtilis. They are terrestrial or gut microbiota bacteria. If you watch my other Reef recap, I think it was last week or the week before, where I talk about probiotics and kind of what a coral probiotic would look like and break down the common products, I think that it could prove problematic to add these terrestrial strains of bacteria in high concentrations to our systems over a period of time. I would probably not add your Microbacter 7, your whatever the hell, Super Probio Mega 19, right? Like they've all got different wacky names that are in some extent of that. I would probably not add them like if you get live rock and live sand. I would let the live rock and live sand do what it's doing. And there's just, there's no data to support long-term that adding Bacillus subtilis or Lactobacillus to our systems is going to be doing any good. In fact, I think they could probably be doing quite a bit of bad, as if those species do persist in our systems, they likely compete and consume the same chemicals and metabolites that many of the good bacteria eat, which could lead to the microbiome shifting in unfavorable ways. So I don't really add any bacteria on the market. Besides, I think the Hydrospace stuff is fine. You can overdo it. Could different fish with different diets add different bacteria from their gut microbiota through poop? Probably. That's something I've not seen a lot about, but I have seen some products talking about fish probiotics. Yep, EcoBalance is Bacillus. Yes, it is. Telegram will have a lot posted pretty soon, but yep, it's all Bacillus, man. Like literally, like here, I'll show you something crazy. If you did not catch the last episode, I think that this is what happened, right? So check this out. Coral probiotic for sale. Look what comes up. Pure culture of lactobacillus. So human-associated probiotic and lactobacillus cultures, like if you buy them commercially, are like $8. And that's like the cheapest thing ever. Same thing with Bacillus subtilis. I think these companies stopped at, the aspect of seeing the word probiotic. And then they said, all right, here's a probiotic. Let's throw it in the product. And they did not stop to ask if coral associated, saltwater associated, any of that was worth it. They just wanted to get the cheapest bacteria associated with the term probiotic to the market as possible. Yeah, milk bacteria. Yes. That's the thing. Like Benepets has this video. I'm not trying to bash them in particular. Every company does this. They are not unique. But they have this video out where they're like, here's how we chose our bacterial strains for like our new Benepets food. They're all coral associated. We did years of research. Then you go on their website and it's like, contains Bacillus species. Like, no, you didn't, man. It's just like blatant BS, Like, no, none of these companies are, none of them. Like, I'm not even just singling out them. Like, they are all so full of it and take advantage of people's ignorance when it comes to the microbiome stuff. Like, like they literally, like, that's like blatant, like maybe I'm wrong, right? Maybe there are coral associated bacteria that are, in that, but I doubt it. Like at least they don't claim it. What did I do, Seascape? Tell me what I did. Sean, send me that paper, please. That's cool. But yeah, I mean, I think like this is something I talked with Tyler, Inland_Reef about quite a bit. And we were talking about the potential for like mangroves, right? Oh yeah, I'm not bashing them as an entire company, right? Like I just think that it's BS that they say we spent all of this time getting coral associated probiotics, and then they're like, here's the bacteria in here, and it's Bacillus subtilis, right? Like I'm not going to bash a company unless it's earned, right? I have no reason to go and bash something I don't know for a fact. But if they're publicly stating two things that are contradictory, they just lied to our faces, right? Like that's something to call out that I feel then I would be comfortable telling that to the owner of Benepets. And maybe he can tell me that actually it does contain these coral-associated strains, and we just didn't put it in our website because people wouldn't have known what we were talking about. In which case, that's great. Maybe Benepets is a great product. I am just pointing out the obvious of the fact that their video says this and their website says something different. And I think that that's something worthy to point out. So if that's bashing a company, then, ban me, right? But I'm going to speak my mind, and, I'm not tied to money. I'm not going to be a sellout in that way. I'm going to say what I think, and I'm going to be honest about it, and I'm going to call it how I see it. And I think that all of these companies are just as guilty of saying coral probiotic. It's literally on the bottle of all these things, and they're terrestrial bacterial strains. It's all about the money, or it's about ignorance, or it's about both. And it's not exclusive to just them. That's just a very obvious example I can pull from. So, lash me if you will, but I guess I don't care about the opinion that companies have about me. I care about likely what the data says and the health of the coral. And, so be it. I'll talk the same way about LEDs and the limited spectrum they have, and probably how that's bad based on the data out there. I think that many things in this industry are likely not based in data and are instead based in ignorance and greed. And there's a lot of companies that take advantage of people's ignorance and just make money off of it. And I think that's problematic. And that if we want to start going this tirade, now that I'm talking about it, if we want to advance this hobby, we need to be transparent, and we need to have education based on what is known in the realm of science. We need to take peer-reviewed data, look at it, look at what is the best for coral health in terms of what restoration facilities are doing, what any place is doing that's researching coral, and then we need to apply that to our products. And we need to begin asking questions. Why is this company pushing this to us if none of the data matches what they claim is good for coral? Why should we blindly trust companies that have a product they are pushing to us for profit and take what they say as face value as true? Like it's a healthy dose of skepticism that shouldn't just be applied in terms of reefing, but probably writ large everything like in our lives, right? Like, I guess that's how I've always been is skeptical, because I don't know, like I would like to see the data. I have not visited any restoration facilities, but I don't think that disqualifies me from having this opinion just because I have not personally had experiential knowledge of a coral restoration facility. I don't think that means that I cannot logically deduce that what companies are doing is bullshit. like, that's that. So I would love to go to some coral restoration facilities. If someone's got some connections, let me know. That'd be awesome. That'd be a dream come true. I would like to do. Okay, well, if you think that I cannot have opinions, I don't know. That's okay, man. We can agree to disagree, and it seems that seems to be a common theme between us, and that's okay. You're entitled to your opinion, and I am entitled to mine, but I feel that just because I have not stepped foot in a coral restoration facility, that doesn't mean that any of my opinions are invalidated in any way. So that's that. Okay, let's look at the rest of these questions. I went on my tirade there. I saw a couple of other ones. Okay, ACF951 said, how do we know if dosing live phyto is actually beneficial? I stopped dosing for a month, and I haven't noticed any difference. So I think that there are a lot of studies, and I can drop some links in here shortly, that the coral will selectively uptake a lot of phytoplankton species. Now, the bulk of coral heterotrophic nutrition actually comes from bacterial plankton, the picoplankton. And there's a lot of really, really good studies about that. So controlled settings to where they have individual frags and colonies in controlled, like little tanks, sterile water, and they add in picoplankton. Let me see if I actually have it pulled up. I was sharing this with Sean Ono. I sent it to him, and we were geeking about how in-depth this paper was. It was like someone's thesis overseas. I forgot what country it was, but I mean, it was like truly impressive work. Okay, I found it. So check this out, right? Now, there's been similar studies with phytoplankton. Let's see. Present, share screen. Okay, so check this out. Feeding on pico and phytoplankton by corals from Okinawa. So yeah, it's in Japan. 113 pages is this dude's whole dissertation. But check out how this is like some like very, very solid experimental design, if I can find this here. And the data is phenomenal. It's like all as a function of time. I got to scroll down to it. Okay, so here's the setup, right? So they've got these individual jars with sterile water. It's all through like peristaltic pumps, right? And they've got pure cultures of all of this different picoplankton concentrations. And then, so that's the number one, right? So they're feeding them like over like a 24-hour period for weeks at a time, just this picoplankton. You can see it here. So like there's different like smaller like cyanobacteria that's very, very, small micron size. It was with Probiotics and Digis were the two species they had. And then they also changed the temperatures. They had kind of unhealthy temperatures and healthy temperatures. So where's the big one where they put together all of the data? They then measured the basically density of protein formation as well as average growth. Where is it at? There's so much data on this. I'm going to have to scroll so far down. That's almost it. There's one that's a function of time. Oh, man, did I skip it? Okay, so yeah, basically here is the net nitrogen and organic carbon concentrations as they change in response to protein concentrations directly correlated to the addition of picoplankton as a function of time over different temperature gradients. Like they measured everything, man. And you can see, yeah, here it is right here, right? Like you can see basically like healthy versus bleached. There is a decrease in concentration of like protein acquisition over time. Like this is over a 6-hour period. I mean, this is like crazy data, right? But there's similar studies with phytoplankton as well. And it's not as basically as large of an effect on this. Mostly phytoplankton is going to contain, fatty acids and things like that. But this is picoplankton. This is dosing specialized bacterial families that we don't have, as a product right now on the markets. This is like the Pelagibacter acae or like nano waterborne, like symbiotic strains of cyanobacteria. So this is what coral are actually eating in the wild. And these are things that as of right now, there is no product to replicate. So all of these advantages we're likely not capturing. And I think this is likely why we have issues with things like Sclerionepthia and Dendronepthia and other NPS, is because likely this small of a micron size of food source has not been able to be reared effectively in a pure culture to where it's a product. So phytoplankton could have, some of these benefits, but it's not going to be as much as this. And also it's a question of the density of the phytoplankton. So if you're adding like 5 drops a day or even like 10 mils a day, like the whole TSA dosing guide thing they have on their website, then I think that's probably not enough, right? You would need quite a large concentration of phytoplankton per polyp to really reap a lot of those benefits. And we don't really have the data on what that looks like. So I think, though, in the future that we will likely have a combination of picoplankton and phytoplankton, so bacterial plankton and phytoplankton that are different micron sizes and they're different nutritional content. So one will have fatty acids, one has the protein covered, and that will provide a more holistic version of coral nutrition that is a live food. And both these things also have bioremediative properties to where they can consume, excess nitrogenous waste or phosphorus in the water column and help maintain, lower nutrients in the system, which is closer to actual natural seawater. So the thing is that there's this whole Darwin's paradox to where on a natural reef, there's relatively low organic and inorganic nutrients in the water column, which doesn't make a lot of sense because there's such diversity and density of life. But likely why some of those, values are low is because the just absolute density of living bacterial plankton that are rapidly consuming it. So all of that excess nitrogenous waste, carbon is uptaken in a living organism, which the coral then feeds on. So if we have that constant influx of live food at the right micron size and the right nutrition, then we could probably chase ultra low nutrients successfully and probably not bleach out corals or have, the negative ramifications we have right now. It's this mismatch between nutrition and our basically aqueous nutrient values in our tanks right now. Because we don't have the actual biological nutrition, we have to rely on corals' ability to take up inorganic nutrients in the water column. And that's a little bit less efficient or less, beneficial way for them to get those nutrients. So they can take up ammonia, they can take up phosphorus from the water column, but they would probably utilize those compounds more effectively by taking them in heterotrophically through bacteria and phytoplankton. And yeah, like Chris said, with minor and major trace elements, that's also a very big part of this. So like I say, I think correcting the microbiome and having management there, getting picoplankton, which can be readily processed and you have pure cultures of in the right species, and then getting traces down even better. Those three things would allow us to grow leaps and bounds in terms of the hobby, and would probably allow us to get closer to natural seawater than like anything else out there right now. I think one of the reasons we have to deviate from natural seawater as much as we do in some instances is because we don't have nutrition down. So that is the plankton angle. Like I say, phytoplankton, who knows how many cells per day are needed per polyp. That's not stuff that I know off the top of my head or even know if there's data for. I mean, it maybe has some benefit. Picoplankton definitely does, though, and that's something we can't capture right now. Okay, second question. Since most of us do have an established reef tank to get rock or sand from, would getting some rock or sand from a vended source that comes from the ocean be a good alternative? Yes, I think so. There's obviously a risk that comes with that, but you also have the benefit of introducing a lot of these families that come in that otherwise would not. Salem, do you have any Aquabiomics analysis of your systems? I actually do not offhand right now. Let's see. I'll be sourcing live rock from Australia in the future. Yes, I've got some Aussie live rock. Seachem has a nitrifying bacteria solution called Stability, and the bottle says for fresh water and salt water. It made me squint my eyes. Yeah. So it's like Dr. Tim, his dissertation was on like the phylogeny of nitrifying bacteria in terms of purely saltwater strains, and he categorized and taxonomized a lot of that, and then one and only he patented, and those are actually those strains isolated. So I'm sure at this point there's other saltwater nitrifying strains that have been bottled up, but I at least know that Dr. Tim's one and only is legitimately like saltwater associated nitrifying bacteria. I've always wondered if phyto, supported by a more holistic food web, where secondary and tertiary nutrition was a benefit to corals. Yeah, so that's the thing, is having that whole trophic level of nutrition, right? So corals can uptake the picoplankton, they can uptake phytoplankton, and then they can uptake zooplankton. And all three of those together, plus the combination of the inorganic nutrients, and then having all of the traces in order to support the nutrients they get from the microbiome, all of that combined gives corals the nutrition they need, plus the zooxanthellae, right? So corals have many, many ways through which they, get their nutrition. So, yeah, I think just adding one on its own, you're not going to capture all those benefits or see a ton of the difference. But in a future world where we have all of those tools at our disposal, I think it'll be a night and day difference. Do you know which strains are in Fritz Syme 460? I have no idea. Probably Bacillus. That's my answer for all of them, because it's the cheapest commercially available strain from any third-party company that's willing to make you a bacterial blend. And that as well. So yeah, that's kind of my thought on all the bacterial products. Like I say, if you want to know more about that, I did a whole live stream last week or 2 weeks ago about all of that. So yeah, any more questions for anyone? If there's no more questions, I will probably call it a night, and I will go work in the lab. So if you want to hang out, though, we can hang out. But yeah, I will probably do some lab work, I would say. There you go. Yeah, Sean's the guy. Yeah, so 60 to 66% is zooplankton. So the rest of that percentage probably, comes from pico and phytoplankton. I would say that if zooplankton really is that high of a percentage on average for most corals, then likely picoplankton would be kind of, next, and then phytoplankton would be like the least likely to be uptaken. And that they are, though, but I think they need the other two to have full nutrition. They're mostly just fatty acids. Like, T-isochryces, a lot of fatty acids, not a lot of protein. You got like the red strains where you get carotenoids and things like that, but that's a little bit different than from like the diversity of proteins that a lot of these bacterial food sources would have. So yeah, that would be pretty cool to see. I would definitely like to see someone do Aquabiomics over a course of time with curing live rock. Like if you get it to where it's not shipped wet and you go through like the old school curing process, I think that'd be pretty interesting to see how that community can change, because it likely would change substantially. So, yeah, like I said, along with like the carbon dosing stuff, that would be something else that we could look at in terms of future experiments. Something else I'd like to do is measuring the microbiome of live rock from different locales. So like, Aussie, Caribbean, Indo. I saw a guy bringing stuff in from Ghana, like African live rock, so to see if there's actually a substantial difference in the microbiome from those different environments. Who knows? How do you quantify the other organisms that consume it and then have a trickle up, such as a protozoan eating phyto that is then a prey item? So yeah, that's the thing is, in like the actual ocean, there's such complexity to the food web at all trophic levels, where all of these things likely feed into each other in terms of the nutritional benefits, right? So if you've got like a rotifer that eats phyto, there's and then like something else eats the rotifer, then the coral eats that. You're getting implicit nutrition from several different levels there. So if we were to take a lot of that and apply it to the hobby, like let's say we have a world where we do have picoplankton, then maybe a reasonable or a more efficient way to get these types of planktonic food sources to the coral would be to use something like a rotifer as a delivery mechanism. So they're looking at rotifers already in the wild as a delivery mechanism for coral probiotics, right, affecting stressed and bleached colonies. And yeah, that could be something that we could utilize. If you could feed them picoplankton and phytoplankton, and there's a lot of evidence that rotifers have a relatively slow digestion rate, so those cells actually stay alive in the rotifers. Then you feed the rotifer culture to the tank, and then you kind of get all three trophic levels in one little living pill, so to speak. So that'd be pretty hard to quantify. It'd be something to play with. That'd be like something like Chad from Reef Nutrition spends a bunch of money working on. But I think there's a lot of potential there, and there's a lot of existing data that shows that that could be something plausible. Let's see. I wonder if pH dropping overnight increases stress and bacterial infections. I notice corals happy during the day and suddenly have issues in the morning when lights out and pH declines. So, I mean, any substantial swing can cause those issues and cause associated stress. It depends on how large that dip is. But also pH below 8.4, there's really just corals have evolved for so long at a pH around like 8.2 to 8.4, to where if you bottom out at a relatively low level, especially if you're not dealing with aquaculture corals, if you buy corals from that are maricultured or even wild, then likely you're going to have them be more susceptible to stress that they are not associated with in the wild. So yeah, that could definitely be something. I mean, a more like a higher stable pH is key to so many different like metabolic functions, including a lot of the immune responses too. But yeah, like Chris said, kalkwasser. Get some calc and run it at night. Drip it heavier at night, and you won't have that problem as much. I mean, even if you're just bottoming out at 8, that's so much. It's just exponentially better to be bottoming out there than like 7.8. There's a night and day difference between what that 0.2 does in terms of coral health and growth overall, even as you're low. So kalkwasser is awesome. Yeah, I definitely do like Chris's method of dosing by pH, but I will say that you got to have a lot of coral to sustain it. So like I've got quite a bit of stony coral, and even in my system to dose by pH and maintain a flatline pH, I still don't have enough calcification occurring. So my alkalinity was really, really outpacing the pH to the point where it's like, okay, precipitation might happen. So you got to really know what your growth rate is and have the correct density of coral that's actually growing in your tank to pull that method off. But if you've got it, if you're farming coral, you've got a very packed system, it's definitely, I think, a very good method to utilize. And then, yeah, you can, if you're responsible, you can toy with sodium hydroxide as well. But that's a pretty caustic one, and you always want to be careful when mixing it, as with everything. But yeah, 13 plus in a wild system. That's crazy. I guess if the pH is stable, they probably don't have too much of a hard time acclimating, though. That's interesting. Okay, Chris, do you want to hear about my thoughts on UV? I'll tease it. I was teasing it last time, and I'm going to have an article about it next week, but I've got a theory for why UVA, UVB is is a good thing from halides and why it benefits coral. And it deals with the microbiome. I found some data behind it finally, because I've been rubbing my head for a long time with UVA, UVB, and the benefits of it. Because, like, you got people like Dana Riddle that kind of push back against it. And they're like, it'll stress out corals. They produce these different proteins, which are bad. But the solution is not bacteria. I think it's fungi. So there's a lot of coral-associated fungus and molds, which are beneficial and deal with nutrient cycling. And many of these, I found a paper, and when you have higher exposures of UVA and UVB, so like acros at the top of reefs, they typically will have higher concentrations of these fungal symbionts, because the fungus will create mycosporin-like amino acids, which are a UV protectant, and they will grow in concentration with higher exposure to UV. And then that in turn has many benefits to the holobiont, because they produce metabolites that regulate the microbial populations, and they also help consume excess nitrogenous waste. And when they grow and they break down larger molecules from the water, such as like a lot of there's some calcium-based compounds that they broke down, and they break down those complex metabolites into simple ones, which then acts as a carbon source for localized bacteria in the coral's microbiome. So I think that that's kind of the missing explanation we've had, and one of the reasons why the UVA and UVB from T5 selective bulbs and halides really has such an anecdotal effect of being much, much healthier for corals, is maybe we're looking at this from the wrong angle, and it's not the bacterial symbionts, but the fungal symbionts that are upregulated, and that those in turn have a lot of effect on the bacteria as well. So I've got a big write-up about fungal symbionts and things like that, but doing the research for that article, I came across that and was like, that's pretty interesting. So that's what I think about UVA and UVB now, and why it might be important in terms of our writing. But obviously, you got to prove it. No, we do need the sun. Are you saying that's what the competitors are saying? But yeah, maybe what I'll do. Okay, I think this would be an easy way to do it, right? So let's get some corals that have only been they've been aquaculture under LEDs for multiple years, like a green slimer, something that grows fast, and we can homogenize them up, and we take an 18S sample, and we can see the fungal populations inside, and then the concentration of those. Put them under halides for like a year and a half, 2 years, and then take the sample again, and then see if the fungal population has changed. That'd be it wouldn't be like completely correlate, that wouldn't be causation by any means, but it would be interesting to see if there's a shift there. And I think that there might be, but I got halides, you got halides. Let's get some LED grown corals, and let's see what happens. I think it could be fun to experiment with. It would be a nice little write-up to do after we get a large enough sample size to do it. It'd also be pretty inexpensive to do as well. We could look at the bacterial population as well, but that's like a lot more likely to change, based on every other parameter. So I think that that'd be the way to do it, is just look at fungal and have before and after. And it's like a paired t-test, to where it's the difference between the two samples over a course of time. And we could do statistics if we get enough data. So I think we should do it. Let's see if halides grow the fungus or not. Does anyone else run metal halides or T5s? See, maybe it takes that long for the fungus to grow again. I don't know. Like I say, this is just all headcanon. This is just like a goofy idea. Who is that, Seascape? I have not heard of them. Do they have a social media? Katharina. This is ecologist. Okay, cool. Oh, she works at Ames. Okay, there we go. Yeah, this seems like someone to contact on this question. Very cool. Yeah, I can talk to Mr. Erickson and try to get in contact with her. That seems like a very good connection for this. All right, S2, do you wanna mess around with growing some fungus then? I don't know. What's up, Ben? I don't know if you were here earlier. I went over your Aquabiomics results, though, and talked about some things for sure. But yeah, I'll probably call it a night if no one else has anything they want to talk about. I kind of gave my spiel. We answered some questions. I'll probably go to the lab. So if there's any last questions, let me know. If not, I'm going to go do some work. So this is your final call. I'm sure she can. That's very funny, Kalamazoo. Kalamazoo is referencing this right here, which is a video game called Halo. This video game we both love, that we both grew up with. Probably the best game of all time is Halo 3. That's not even a hot take. I think it's that's the opinion. Oh no. What about them, Ben? I figured you were gonna mention that on your report. That was a weird one that you had. That I think that might be coming from Fiji, maybe, because Eli mentioned that he's been seeing them a lot more on different tests, and they've been rising. Yeah, so I gotta really think about how you might want to resolve that one, because the thing is they're Cnidarians, so anything that's going to take them out is likely going to take the coral out as well. So, I mean, likely your best strategy is just shoring up like the general health of the corals in the system and keeping stability, which is like boring. That's a boring answer. But I mean, dude, there's not going to be any type of selective, like, inhibition or elimination that you could do to wipe them out that wouldn't also probably nuke all the coral in the tank. Yeah, that's one that Andrew, Eli, and I need to go and have like drink some coffee and think about, because that's a really interesting problem that's starting to arise. It's not like reared its head in like a really ugly way yet, but there could be some that pop up that could be quite virulent, that just we haven't had the bad luck of getting them yet. So yeah, like I say, I think a lot of them are aerobic. I don't know. You'd have to find like a drug target for them that's so specific to them. I don't know if you could. That would be someone that would know more about them. You need to find like a specialist with them. I only know like cursory knowledge about them, and it's certainly not my wheelhouse. But yeah, they're definitely something to keep in mind, but I would not lose sleep over them right now, especially when you have the bigger, more obvious issues of the microbiome, the bacterial side of things in front of you. But yeah, they're weird. What would yeast extract do to fungus? In terms of like trying to grow fungus, like culture them, like yeast extract in terms of like making an agar, or what are you talking about, Matt? Something you could do with them is maybe try to filter them out of the system. Like you could do like really, because a lot of them are waterborne, or could be, depends on the species. You could try to have like lower micron filtration depending on the species. I don't know if you had species level resolution on that test you sent me, but like they're like from like 10 to like 450 microns typically. So yeah, a lot of like existing filter socks could probably take them out, which could maybe help the levels if you happen to get lucky and you have a waterborne one. But yeah, they're such weird animals, man. But yeah, I'll probably call it a night then. I'm going to go to the lab. I'm going to have some fun. I'm going to play some Halo. I appreciate you all tuning in and staying with me despite Remy not being here and running the computer very, very smoothly. But yeah, thanks for tuning in. Be sure to tune in next week for another Reef recap, and I'll see you then. Have a good night, everyone.